We will continue with our topic on coastal protection. The armor unit size is the most important component of the rubber mold structure, and its sizing will first be determined, and subsequently it will dictate the remaining geometry of the structure, which includes the layer dimension, the sublayer unit size, the structural slopes, the crest width, etc. Our unit is characterized by their specific gravity, their size range if it is from quarry stones, the shape, and thus its interlocking property. Its stability is highly dependent on the shape, the placement method, whether it is arranged or whether it is dumped in place, the type of attack, and also the location of the armor unit, whether it is positioned at the head of the breakwater, which is subjected to more severe condition, or whether it is placed at the trunk. If quarry stone of the required size cannot be obtained at reasonable cost, then precast armor unit may be chosen for rubber mold structures. Here we see some of the common precast armor unit design, such as a tetrapod, dolos, and tri-bar. This precast armor unit typically has much higher stability coefficient (KD), and hence a smaller size can be used in place of a quarry stone to achieve the same stability. However, precast armor unit may also be more prone to damage. This figure here shows example of precast armor unit which are dumped in place. Over here we see example of precast armor unit which are arranged in place to achieve higher interlocking properties and thus achieve much higher stability coefficient. You can see the size of the armor unit compared to a human. Remember that if a quarry stone is used, the size required will be much larger due to poorer interlocking properties. Right now we are going to look at the Hudson's equations, which is important in the selection of armor unit. The equations give the weight required on the left hand side, which is a function of the specific weight, the design wave height to the power of 3, the stability coefficient, the specific gravity in air, and the phase slope. Based on the equation, we are able to tell that the higher the stability coefficient, then the lower the weight of the armor unit required. Also, the more severe the wave condition, the larger the weight of the armor unit required. Since h is to the power of 3, then we can expect that when the design wave height increases, then the weight required will increases to the power of 3. If we are using quarry stone, then usually more than 50% of the units must have the weight more than the W value that is calculated. The equation can be rearranged to provide the stability number of the armor unit, whereby the stability number N can then be written as H divided by the expression over here. This can also be written in this form based on rearranging the Hudson equation. This slide here shows the typical stability coefficient values, KD. Consider two layers of unit randomly placed with zero allowable damage and minor overtopping. Then the stability number for different armor unit at the trunk and at the head for breaking wave and non-breaking wave condition as shown in the table. Based on this table, we notice that if the armor unit is subjected to breaking wave condition, then the stability is lower. If we compare quarry stone, which is smooth and rough, a smooth quarry stone will have a lower stability number compared to a rough quarry stone. Precast armor unit like Dolos, Tetrapod, and Triva generally has much higher stability numbers. In rubber mold structure, by allowing for damage, the same weight can then be used for a larger wave height. Here we define the allowed larger wave height as H prime, whereas the zero damage wave height as H. So if we use a armor unit of weight W for a larger wave height than the zero damage wave height, then H prime over H will be a number which is more than 1 as shown in the table. The ratio of allowed wave height compared to a zero damage wave height can be determined based on the type of armor unit and the percent damage, which is defined as the percent volume of the armor unit which is allowed to be displaced from the critical zone that is at the trunk of the breakwater downward to a depth of H below still water level. For example, if we allow 5 to 10% of the armor unit to be displaced by a depth of H below the still water level, then we can use the same W for an allowed wave height which is 8% higher in the case of a smooth rounded quarry stone. But if we allow up to 50% damage, then we can use the same weight of armor unit for a wave condition which is up to 1.54, which means 54% more severe. This slide here shows example of the design table provided by USACE's Coastal Engineering Manual. Let us now look at an example. The head of a rubber mold breakwater that is to be constructed on one of the Great Lakes is to have an armor face slope of 1 to 2.5. The breakwater head is in water having a design depth of 6.6 meter and the bottom slope fronting the structure is 1 to 30. The deep water design wave significant height and period are 4 meter and 7.3 seconds respectively, and it may be assumed that the refraction coefficient from deep water to the structure is 1. That means there's no refraction. Assume that the breakwater will have only minor overtopping for the design condition. Determine the required armor unit size if angular quarry stones and tetrapods are to be considered. Assume S equals to 2.65 for the stone and S equals to 2.4 for concrete. First and foremost, let us find out the design wave condition. We are given that the wave height is 4 meter and the wave period is 7.3 seconds. But these are information at the deep water. So based on this information, we are going to determine the design wave height. Assuming that we are going to design based on H10, the 10% largest wave, the H10 is equal to 1.27 of the significant wave height, assuming that the Rayleigh distribution applies. And so for this particular case, the breakwater will be designed for a wave height of 5.1 meter. But this 5.1 meter is still at the deep water position. So what we do next is that we use the wave period to determine the deep water wavelength, so that we can find out at the breakwater, where water depth is 6.6 meter, the wavelength is 53.8 meter. The n equals to 0.84. The shoaling coefficient equals to 0.96. Since the refraction coefficient equals to 1, we only need to consider the shoaling coefficient. And thus, for the H10 of 5.1 meter in the deep water, after shoaling, the wave height will be equals to 4.9 meter at this location with a water depth of 6.6 meter. We can also find out whether this wave is going to break at this particular water depth. Since we know that the bottom slope of the beach in front of the structure is 1 to 30, that will give us m equals to 0.33, the beach slope. So for a deep water unreflected wave height of 5.1 meter, we found out that the breaker height will be 5.6 meter and the breaker depth will be 6.9 meter. That means in this case, the wave will break at a water depth of 6.9, meaning that it will break before it reaches this location, and thus the wave at this particular location is a non-breaking wave. We're now ready to apply the Hudson's equation. We will first consider the zero damage condition with non-breaking waves for the structure head. We will be considering both angular quarry stone and tetrapods. The stability coefficient for each of these Armour units are obtained from the table presented previously. The weight of the quarry unit required is next calculated. So we have the specific weight given here as 2.65 multiplied with 9,810. We have the design wave height of 4.9, which is the same in both cases. For tetrapod, the specific weight is 2.4 times 9,810. This is the stability coefficient for each Armour unit. S is 2.65 here and it's 2.4 here, and cotangent theta is the slope of the rubber mold structure, which is 2.5 at the head. So from this, we obtain the weight of angular quarry stone required as 97.3 kilonewton, whereas if we use tetrapods, the weight required is only 73.4 kilonewton because tetrapods has higher interlocking characteristic and higher stability coefficient. Next, we consider the case where 10% damage is allowed. From the table, we obtain that the H prime over H ratio is given as 1.13. In this case, since our design wave height is 4.9 meter, by dividing 4.9 by 1.13, we get 4.3 meter, which means that we are now going to apply the Hudson's equation using a wave height of only 4.3 meter. Since we design only for 4.3 meter, if the rubber mold structure is exposed to the actual 4.9 meter wave condition, then we expect that it will suffer 10% damage. Right now, we perform the calculation again by changing only the H value in both equations. If we use angular quarry stone, the weight required is 65.7 kilonewton, which is less than the previous slide because of the 10% allowable damage. If we use tetrapods, then the weight required is even lower.